Okay, so welcome back to the Virtual School of Computer Science, Computational Science Engineering Summer School. And we're going to be having the first keynote for this year's summer school. There will be 3 keynotes. The first keynote is going to be on the algorithm aspect. The second one is going to be on the future hardware roadmap. And the third one is going to be from the applications perspective. So for the first keynote, we're very, very lucky to have Michael Garland, who is one of the, I would say, the very well-respected expert in algorithm design for GPUs. And Michael was a former faculty member with the University of Illinois. It was one of our biggest losses, and NVIDIA's one of the NVIDIA's biggest gains. But Michael graduated from Carnegie Mellon with PhD, and he spent a few years at Illinois working on graphics. And then after he moved to NVIDIA, he started to work on the more computational aspect, especially working on some of the tough algorithm challenges when using these GPU computing devices. And his most, I would say, arguably his most recent, well-known work is in the area of sparse matrix computation. And chances are, if you use sparse matrix code for GPU, you probably have either, knowingly or unknowingly used either his method or his software code base. So, I think he's also looking into other types of challenging algorithm problems, such as graph algorithms and so on. So I would like to encourage you in the next hour to take advantage of his insight, and he's going to have plenty to say, but also make sure that if you have some good questions and so on, do ask Michael, because this is a great opportunity to tap into his insight. Okay, so Michael, without any further ado, Michael Garland.
Thank you for the flattering introduction. And also thank you to the folks here in Minnesota that you can't see who actually set this up for me so I could come and give this talk so smoothly without having to come down there to Illinois. When May said in the next hour, but I think I have an hour and a half, right? Okay, good. So my goal today is to try and give you some idea of how you might think about approaching the problem of algorithm design on GPUs. Because once you learn the mechanics of writing CUDA programs, the next interesting question is, how should I think about some problem that I want to solve on a GPU? And I would argue that in many cases you want to think about it perhaps a bit differently than you would in a CPU, or if you haven't programmed parallel machines before, you might be unfamiliar with how you might want to approach these problems. So I brought along some slides that show a couple specific examples of code I've worked on for sparse matrix vector multiplication, which Wenmei alluded to, and some reduction code. I'm going to show you some code because I think it helps make things concrete, and then you can go back later and try and understand it, but I'm not actually expecting you to understand every piece of code I'm going to show you right now. So I want to start out with the high-level things that I want you to really remember. So I think part of the challenge of programming new processors is to achieve the right perspective on how to approach the problem of programming them. So this is my opinion about what the most important perspective points are. First of all, I think it's very important to mentally condition yourself to think about GPUs as parallel coprocessors and not as accelerators. Accelerators, thinking about them in that term and using that word, leads to, perhaps unconsciously, program design that involves writing code that looks like, my program lives on my CPU, I occasionally copy data to my GPU, do some small computation on it, and then copy it back. And there are perhaps software engineering reasons that you might want to port legacy code in that way, but you cannot expect that you'll ever get reasonable performance that way compared to the right way to approach the problem, which is you should think about it as a coprocessor. You should place the data where you're going to operate on it, and you should leave it there for as long as possible, until you just can't leave it there anymore. So I'm going to talk to you, for instance, about sparse matrix vector multiplication. And one of the reasons for doing that computation is to build iterative linear solvers using, say, the conjugate gradient method. And it would be a very bad thing if you designed such a solver such that every time you performed a matrix vector product, you copied data over to the GPU and copied it back. The goal in building such a solver would be to put the entire problem on the GPU, and for the entire lifetime of the solver, just iterate on the data there on the GPU. So that's an important point to keep in mind. The parallel problem should live on the GPU, and you should be very loath to pull data back to the CPU unless it's absolutely necessary. If your problem is mostly parallel, think of your CPU as the I/O accelerator for the GPU, which is the computational engine. I'm sure you've heard it already, and you'll probably hear it again, but one of course, the fundamental issues you need to deal with when programming GPUs is that they expect to be given programs that expose lots of very fine-grained parallelism. And getting any kind of reasonable performance usually requires that you expose a lot of parallelism. But you shouldn't take that to mean that you should always expose the maximum amount of parallelism. In many cases, it's important to expose enough but not too much. And I'll show you a couple examples in my slides where actually exposing too much parallelism could be harmful, and you'll get better performance by having less. Fundamentally, the issue is this. If I have many, many completely independent tasks, then obviously they can all be performed in parallel, and I can have as much parallelism as I want based on the size of the data I have. But if I ever need to coordinate results from many tasks, there's some cost involved in combining results and coordinating tasks. And whenever I have that kind of coordination cost, that will increase with the number of tasks I have. And so I need to be careful that I don't increase the number of parallel tasks so much that the coordination cost becomes prohibitively high. Obviously, I'm sure you also hear many times this week that you should try and keep memory accesses regular. And this, of course, is very important. But you should also keep some other things in mind, which is frequently, in order to organize the data well and also to get good algorithmic performance, it's good to look at divide and conquer methods. And they frequently give you regular access patterns. But the fact that we constantly tell you that irregular data layout is bad and thread divergence is bad and divergence in memory access pattern is bad, well, that's all true. But that shouldn't mean that you should be deathly afraid of any and all irregularity. Because the truth is that irregularity is perfectly fine as long as it's uncommon. As long as the common case can be regularized, the performance will be very good. And the sparse matrix vector stuff I'm going to show you is a perfect example of that. When thinking about CUDA programs and thinking about the things I'm going to tell you today, this is the picture I'd like you to have in your mind of what the CUDA model of parallelism is. Essentially, it's a virtualized version of a high-level view of what the processor is. Fundamentally, we want to create a lot of parallel blocks, which you could think of as sort of a virtualized multiprocessor, each one of which consists of a lot of threads in its own memory. And the consequence of the fact that it's virtualized is essentially that we don't make any guarantees about how they're going to be scheduled on the machine. So when approaching some problem, I think it's useful to think about which one of two broad regimes of parallelism it falls into. The first is where you have many independent fine-grained tasks. A very simple kernel like Saxby or vector addition, where you just have two vectors and you're going to pairwise add all the elements together, is a perfect example of having lots of completely independent, very fine-grained tasks. And whenever you have a problem like that, you're going to expect to assign one task to, say, every thread of a kernel and just launch a whole bunch of threads, and they're probably going to proceed independently. And then the only task really is to make sure that the memory that you access is laid out in a way that you'll have reasonable memory access patterns where possible. The other regime of parallel tasks is where you can actually decompose the problem into perhaps more heavyweight tasks that can be given collectively to an entire CTA. And something like matrix multiplication is a good example of that. You actually want to take the matrix, you want to block it up into tiles, and then give each tile as a task to an individual CTA. And that leads to a somewhat different style of code design. And that's pretty typical in these tiling and divide and conquer algorithms. And I'll show you examples of both of these. Okay, so the first concrete example I want to show you is this sparse matrix vector multiplication problem. The stuff I'm about to tell you is described in a paper that we published in Supercomputing last fall, which you can find online. And a little later in the talk, there's a slide with a URL for the code that implements all this in case you want to go check it out. So here's the problem. We want to compute the product of some sparse matrix A and a dense vector X. And in the particular benchmarks I'm going to show you, what we're measuring is actually AX plus Y rather than AX. But that's an unnecessary detail. So the interesting thing about this problem is that unlike dense methods, I think you've probably talked about matrix-matrix multiplication already as an example of tiling. The matrix we're talking about is extremely sparse. Right? Typically, it'll only have order n entries that are non-zero rather than n squared. And so the goal is to only store the non-zero entries and only perform operations on the non-zero entries and ignore all of the other zero entries in the matrix. So in contrast to dense methods, which are very frequently throughput or computation limited, sparse matrix methods like this are almost universally bound by memory bandwidth. So the goal here is actually not to get anywhere near the peak gigaflops rate of the card. We'll be well below it. But the goal is rather to achieve the highest percentage of peak bandwidth possible. So this is an important thing to understand when you set out to look at a problem, because you need to know, have I achieved success? In our problem, success means we get very close to peak bandwidth, and the gigaflops will just be whatever they are. For something like matrix-matrix multiplication or the DGEMM BLAST kernel, you want to get closer to the peak throughput of the card, and that's how you would measure success. So when starting out, we always want to know how to measure success, right? It tells us whether we're there or not, and whether we need to continue optimizing our code or whether we can break for lunch. So one of the important things to understand about sparse matrix problems is that there are actually a lot of different kinds of sparse matrix problems. In this kind of world, there's basically three different regimes of sparsity patterns, by which I mean essentially what non-zeros are going to be filled in the matrix. The first one which arises from, say, discretizations of PDE problems on regular grids, is what I'll call structured. And basically for methods like this, where the matrix arises from some stencil operation on this grid, what you're going to see is a matrix where all the non-zeros are on some diagonals in the matrix. And that structure is something that we want to exploit in the code. Another basic sparsity regime is unstructured meshes. So these might come from irregular finite element meshes. They might come from graphics meshes like this Buddha statue that you see on the slide. Or any other mesh that's sort of embedded in space is usually reasonably well behaved. It's going to have non-zeros that are scattered throughout the matrix, but they're not going to be pathologically bad. There's going to be usually some meaningful average of row length, number of non-zeros per row, and the variance probably won't be too high. So these are pretty well-behaved matrices, even though they're not completely uniform like the structured matrices. And then there's everything else. Things like power law networks, social networks, the web. These things can be pathologically bad, where, for instance, every row in the matrix has 3 non-zero entries, and 3 rows have order n entries, billions of entries maybe. The reason I bring this up is that to understand how to design the algorithms to deal with these, you need to understand what sparsity regime you're in. And you will, in general, want to use a different method for each of them. And as we'll see, one of the main reasons to think about this is, in fact, load balance. You heard me talk about the difference in these matrices with the number of non-zeros per row. And if you have a good idea of how many there are, then you don't have to worry too much about the load balance between different threads in your program. But if you have no idea how many there are per row, and some might be very heavy and some might be very light, you might need to worry about how you balance the work across all your parallel threads. Any questions about the basic problem I want to talk about before I actually start talking about it?
Any questions?